So what we're going to look at now are something called Turing machines. And what Turing machines are is they're essentially automata, or they are computing. It's a kind of computing program, right, that allows us to do a lot of, an incredibly diverse number of things. And essentially, actually, one of the things called the Turing conjecture states that anything that we can do with a normal computer or, a programmable computer that we normally see inside of like our everyday world, we can actually do utilizing a Turing machine. The difference is that while a computer and its programs, right, what we are acquainted with in terms of a computer and its programs, the programming languages, the understanding of how the programs work is fairly straightforward. Okay, a Turing machine, it really isn't. Okay, how you do it, the ways in which we program and how the programs work are very, very simple. There's not a huge language for it. There's not a lot of semantics or syntax. It's actually very, very basic, and we're going to look at that. But then it really takes a lot of thought and a lot of cleverness to actually program a Turing machine in order to do something like, even, say, for example, determine whether or not a number is a power of 2. Whereas this is actually an incredibly simple thing to do if you are going through in programming. So it's kind of like a trade-off. On the one hand, with the Turing machine, it's the concept, or the concept of the Turing machine is very, very simple, but it's extremely difficult to program. Whereas in the case of our more complex machines, where it's got assembly language and we've got all these different kinds of computer languages, and you've got semantics and syntax, and that's all complex, right? Then the programming of it, though, is a lot more simple, right? It's a lot more straightforward. So what we're going to do in order to kind of help us think through how does computation work and programming work, we're going to look at Turing machines. So let's just first start out with, what do you see when you actually use a Turing machine? Like, what are you going to actually see? So we're going to start out, we're going to have something that's called a tape, all right? And the tape is a sequence of, call them boxes, right? Okay. Or these are, we're going to give them a name in just a little bit. Let's say, for example, they've got ones and zeros. So here's a 1, here's a 0, 1, 1, 0, 1, 1. And then we might have stars, that sort of thing. And that's what you see, okay? And that's what you see. And what we're going to do is we're going to actually assign a starting place, a starting location. And let's say, for example, the starting location is the furthest most left box. And we'll call that Q0. So we're going to start here at Q0, and that's our starting location. Just like any kind of algorithm, we're going to need a starting location, call it Q0, okay? And what we're going to do then is that we're going to then input in, we're going to have a function, and that's our transition function delta, and we're going to input in, say, for example, Q0, and this value here, that 1, and then it's going to give me something out. And what it's going to give me out is it's going to give me 3 things back. All right, and we're going to look at like what are what's the domain of this transition function. We'll look at the range, but let's first just look at this. It's going to give me another state. So this thing, Q0 being the state, we're now going to go on to Q1. We're also going to change or perhaps keep the same the value that's inside of the box. So say, for example, this goes to 0, and so what would happen is then I would make this a 0. And then it would say go on and either move right or move left. And if I'm in the furthest most right box, I'm going to actually, if I'm in the furthest most left box, I am going to, just stay where I'm at. And otherwise, I'm going to move in the direction. So let's say, for example, this one moves right. So I'm now going to switch states. Okay, I'm going to Q1, so I'm now going to be in Q1. And now I change the value in the box that I was in at 0, and I'll move right. And so now I'm in this box right here, and the state I'm in is in Q1, okay? And the value in that box is now 0. So let's say, for example, I now have my transition function, delta, and my new state is Q1, and my input value is 0, okay? And now what I'm going to do is I'm going to get another value back from it. Let's say, for example, I get Q star. That's the next state that I get from there. Say it stays at a 0, so I don't actually change it. And let's say, for example, I go left. Okay? So now I'm moving back. I'm going to move back left. Okay? So I move back here. That's the left. In my previous section, it stayed at 0, so I kept it 0. Okay? And now my new state is Q star. So Q star, notice that Q star is here. The 0 is inside of the location where I was, okay? And then I moved left. I moved left relative to my location. Let's do one more. Let's say, for example, I take my transition function, delta, and I'm going to now take Q star, and now I'm at 0, okay? And let's say, for example, it equals, and we're going to get Q accept. We'll look at that in just a second. Q accept, comma 1, and then move right. So what will happen here is if we kind of want to do it in a more natural order, I'm going to change where I'm at to a 1. Okay. I'm going to move to the right. Okay, so now I'm in this box. I'm in box number 2. And now my state is in Q accept. And Q accept will actually be our halting state. That's the place where we're going to stop. And that tells me that, in fact, that I have found whatever it is I'm looking for. Say, for example, I'm like, oh, is this a power of 2? Yes, it's a power of 2. I accept now. I'm in my accept state. Okay? And so you can kind of see that this is pretty simple in terms of your, like what it is that you're going to do, right? You plug in two values. On the one hand, you have a state and a value for whatever box that you're in. You plug those in and you get out an output. And then the output is stated as another state, a value that you're going to switch your current box into, and then where you're going to move. Okay, so you're going to change states, change your current box, or keep it the same if it still stays the same, and then move either left or right inside of your tape. And that's all you're going to be doing. Now that we looked at basically how it is that they kind of work and kind of understand the functions, you know, the inputs and the outputs, and we'll kind of like make those more concrete in just a little bit. Let's take a look at like how do I know what I'm supposed to do based upon the program. So what I'm going to show you right now is basically a table. And this table is going to represent the function, okay? And so what we've got here is across this top right here, these things here, again, they're called our inputs, and our input alphabet is going to be with a 1 and 0, and we'll talk about that a little bit more. And we're going to represent that with gamma, okay? And so that's the capital gamma. It looks like a little corner. And then we're going to have our states, and here's Q, and you're going to notice here are all the states except not, reject, or accept. So basically, those are the Q, right? And this is going to be, we'll call that Q minus Q accept and Q reject. All right? And so our inputs basically say, okay, so here's the input from Q minus Q accept, Q reject, and here's the one from gamma. And then what we'll get is right here, okay, this location, say for example, that's going to be the output. So our outputs are going to be the values that are going to be inside of these boxes. And so those give me my outputs. All right, and so we'll take a look, and here's our string. All right, and so now what we're going to do is we're going to say, okay, well, if I do that, let's actually begin a program and see what happens. So if I start here, I'm going to have this very furthest most left-hand cell. We're going to start that at Q naught, and let's say it's Q naught 1. So I go over here to Q naught in the Q accept, and then here's 1, and I see that now my instruction, right, is Q1, that's going to be the new state, 0, right. So now I'm going to change this to a 0. I'm going to switch my states to Q1, excuse me, and this was a 0, and I move right. Okay, so now this is my new location. Okay, my state is Q1, and the value that's in there is 0. So now I go down to Q1, I look at Q1, 0, and Q1, 0 is right here. Okay, that's the output state, or the output, excuse me. And so we're now going to see, okay, well, I changed to 0, so nothing changes, it stays at 0. The new state is Q2, okay, because that's what that's stated right there, Q2, and I move right. So now this is my new location, my new state is Q2, and my new input is 0 as well. So now I go down to Q2, and I have a 0, and it says Q1, okay, 1, right. So now I'm going to switch this to a 1. My state changes, it's going to be a Q1, and I'm going to move right 1, so now here's Q1, and I'm now with this 1. So now I look over, and I see, okay, here's Q1 again. I look for the number 1, so here's my new state, okay, Q1, that's, excuse me, Q1, and I need a 1, and then I have a 0 and a right. So I'm going to go to Q1 again. So my state actually, oh, pardon me, that should be a Q2, sorry. Q2, okay, so my new state is Q2, right? I move right, and I change this to a 0. So this is now a 0, right? It's 0. I go move right 1, and my new state is Q2. And so I'm located now with the star, and I have a Q2 there. I look down at Q2. Q2 is now Q reject 1L. Okay? So basically, I'm done. Okay? Because the state now is rejection. All right? So yes, I do change this to a 1. Let's move it left. Okay? But this is now Q reject. And so what that does, that halts the program and says, hey, no, we didn't find what we're looking for, fail, false, whatever it is. We're now in Q reject, we stop. Okay? And so that's essentially how we're going to use one of these. Along the top, okay, we'll see, okay, I've got a set of inputs, or excuse me, a set of our input alphabet, which is part of gamma, okay, or our inputs, and then I have my states minus the rejects and the accepts, because you're never going to, like, once you hit accept or once you hit reject, like, they're never going to be input states, okay? We're never going to make them part of the domain because basically it's stopped, right? So you shouldn't be getting an output if you use QAccept or QReject. That shouldn't happen, all right? So consequently, they're not going to be part of our domain, right? So we're going to take, the Cartesian product of those two. They're going to be our inputs, and then our outputs are going to be a combination of our states, that input alphabet, and then a direction, either left or right. Okay? So let's actually put that all together. So let's talk about the makeup of the Turing machine. Okay? So we have a tape, all right, with elements of our inputs in locations, all right? Only one element per location, and we're only going left and right, so it's only single dimensional, no problem, right? Okay, so that's the first thing that we got. The second thing, all right, we're going to have a set of states, Q, and Q is going to equal, right, basically we'll have, imagine dot, 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 and then a Q accept and a Q reject. In our example, what we had was, we had Q naught, Q1, Q2, Q accept, and Q reject. Those were the elements of our input alphabet. Excuse me, not our input alphabet, but our states. Those were our states. Then 3, we had a set of inputs, and that was, in our case, right, we had dot, 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 and then you're probably going to have something like a star which is basically something, it's kind of like an empty value. In ours, our example had the binary values. It had 1, it had 0, and then it had star. You can actually get input alphabets of lots of different kinds, and just depending upon the kind of program that you're writing, I suppose you can utilize, decimal values. You could use, hexadecimal. You could use octadecimal or octet. It's up to you, right? In terms of the construction, but basically we're going to get this input. So these are inputs. Okay, here are our states. All right, now our domain, okay, we're going to have our domain is going to be Q minus, and remember we can't utilize our accept state or our reject state as part of our inputs. So we're actually going to eliminate those two, and then that's going to cross with the members of our inputs, whether or not, 1, 0, star, whatever, okay? That's our domain. Now, by the way, there's a subset here. If we take, in our example, like say, for example, we have our inputs, and we subtract out, say, for example, star, okay? We get something called an input alphabet. So that is like a set of values all right, that are defined for a particular input that we're gonna, kind of test out. Those are gonna be our testing values. Generally, the empty one is gonna represent spaces, all right, and so consequently, they're not gonna be part of our input alphabet, even though we do have specific outputs that will be associated with, say, for example, star. So essentially, like, this is all the stuff that you're gonna put into the computer. Or into the Turing machine, excuse me. And it's a subset of gamma. So there's our domain, Q minus Q accept, Q reject, cross gamma. And then our codomain is going to be Q. Now, in this case, we can use Q accept and Q reject because these are our outputs. Cross gamma again, okay, cross, and in this case, we're going to have a set just made up of left and right. Because remember, we've got to have that third one that actually tells me where to move. Okay, so my transitional function delta is going to go from Q minus Q accept, Q reject, into Q cross, cross gamma, into Q cross gamma cross, in this case, left and right. And there are a lot of ways that we can actually define what these functions are. They're not necessarily mathematical. Oftentimes they're not. Instead, they are, we'll see them. There are cards that are designed in order to kind of give instructions to Turing machines. We utilized a table, all right? But they all basically look like this, right? Where we're going to have, okay, here's our input state. Here is the member of our input, and our output is going to be a state and an input, right? The next input that gets changed, and then whether or not I'm going to go left and right, okay? And that basically sets up what happens with the Turing machine. And that's basically how Turing machines work, okay? And by the way, this is called a transition function. Okay? And there it is. There's our Turing machine. All right, let's take a look at now a simple program utilizing a Turing machine. And one of the things that we want to notice about this is it's actually really hard to do. Not just the programming, but the program is actually somewhat complicated. The sequence of instructions and how the instructions work really simple, but it's kind of hard to follow in some ways. And that's actually one of the weaknesses of using a Turing machine. It's kind of hard to write programs for them. Let's say, for example, we wanted to determine if a string is a power of 2. All right, so we're gonna have an alphabet, okay, made up of A, X, and star. So our inputs gamma are going to be A, X, and star, and you can see our Q states. We've got Q naught, Q first, Q even, Q odd, and then Q return. Okay, and basically, and then also we'll have a Q reject, and we can have a Q accept, and so there we are. Okay, if you were kind of thinking about how you might actually set up a program, say in Python or inside of Java or something like that, in order to determine if a string is a power of 2, probably be pretty easy. All right, you probably take you take a modulo 2 of whatever number you're looking at. Set it if it equals 0, then then you do something else. If it doesn't, then you're gonna bring back false, right? But you can kind of imagine how this works, and it's not really all that hard. It'll take you a couple minutes. Done. You can figure out that program pretty quick. Of course, like we said, there's, a lot to that. I just said modulo, we'll probably use div, we'll probably use a bunch of different things that we've got to use. It's got to be put in the right places, etc., etc. So the complexity of the programming language, all right, that's your trade-off. On the other hand, pretty simple to set up the program once you know it. So let's actually take a look at this one. Let's say, for example, I have a string, and my string, I'm going to have 3 A's. So we already know that this is, in fact, not divisible by 2, okay? And so consequently, we're like, okay, well, how much work is it actually going to take me to tell me back that, in fact, it's not divisible by 2? We're going to start out here in our leftmost spot at Q naught. So I got Q dot A, okay? And so now I go Q first, star, right. So my A becomes a star. And then I have Q first, and I moved right, okay? So now I'm at Q first. I am, in fact, Q first A. So this is Q first, it goes to Q even, becomes an X, and an R. And I move right, so now I'm at Q even here, and I have Q even A. So I got Q even, I have an A, so that's Q odd. That moves to Q odd, then A. Okay, so that stays in A, and then I move right again. Okay, so now I'm here, I'm at Q odd. I have a star, so Q odd, star, this becomes reject. Okay, Q reject, star, left. All right, so now I moved here, I'm in reject, I stayed at star, so now I've halted, I've rejected, I now found out that in fact it's not a power of 2. Okay, now that's just to determine if like 3 A's is a power of 2. What ends up happening with this particular problem is if I go 4, 5, anything really past like 6, I've got to move back and forth on this tape several times just to determine whether or not I in fact have a power of 2. Okay, do I have an even number or do I have an odd number, right? Okay, and to figure out whether or not I'm going to reject or accept. And so like that whole process can be quite lengthy and kind of hard to figure out why in the world did it work. Like why did it actually happen that when I programmed it this way with this particular set of inputs and outputs, right, this particular transition function, why did it even work? Okay, and that's one of the challenges of actually working with Turing machines is that the programs themselves actually aren't that intuitive. All right, versus once you know a programming language, it's not completely intuitive. I mean, sometimes there's a lot of cleverness that goes into complex programs, but for the most part, it's a lot more intuitive. It makes a lot more sense as to how you're going to get from point A to point B. And when it comes to a Turing machine, that's not necessarily the case. All right, so this actually completes our mini lecture on Turing machines. Hopefully that helps you to understand how they work. So that if you see them and you're reading through them and you're doing some computer science, you actually can follow along.